Okay. Hi, everybody. My name is Bodo Schwabe from the University of Göttingen. And today I want to discuss fuzzy dark matter on galactic scales. So just briefly, what is fuzzy dark matter? You can see here on the upper left, cold dark matter on the right and fuzzy dark matter here on the left are almost indistinguishable on large scales, which is good because then fuzzy dark matter can mimic the successes of cold dark matter on large scales. But as we can see here on the right-hand picture, fuzzy dark matter is very different compared to cold dark matter on galactic scales, so in halos and filaments. You can see here these characteristic interference patterns in the fuzzy dark matter overdensity, and especially the granular structure in halos, and then the solitonic core in the center of each halo. So those will be the objects that I will frequently talk about during this 20-minute talk. And then a typical radial density profile of a fuzzy dark matter halo looks like this here on the lower left, where you can see an NFW-like outer tail and then this prominent inner so-called solitonic core. So some core and fuzzy dark matter originally was one of the solutions for the CAS core problem as well. So on the one hand, you have suppression on small scales, potentially solving the missing satellite problem, for example, and you can also find here a solution to the CAS core problem. So what is fuzzy dark matter mathematically? It's a non-relativistic scalar field, and therefore well described by the Schrödinger-Poisson system. So the Schrödinger equation with a potential that is sourced by the self-gravity of the fuzzy dark matter component, plus potentially additional other densities like baryons, black holes, stars, and so on. And then the density is just the modulus square of the wave function that is evolved by the Schrödinger equation. Since the Schrödinger equation is well known from quantum mechanics, actually a lot of phenomenology that we know from quantum mechanics also shows up in these simulations. For example, I already introduced this wave-like behavior on galactic scales. That's actually on the de Broglie wavelength scale. So the inverse of the mass of the fuzzy dark matter particle and its velocity dispersion, or typically the virial velocity. And these granules then oscillate on the de Broglie time scale, which is just the de Broglie wavelength divided by another factor of the velocity. So these two will be the important length scales associated to fuzzy dark matter. And as you can see here, these lengths and time scales depend on the axion mass or the fuzzy dark matter mass. And therefore, different masses are most prominent on different length scales. And namely, for a mass of roughly 10 to the minus 22 electron volts, this is on galactic scales, on kiloparsec scales or slightly larger. And therefore, for very light masses, actually linear scales are altered, and then you can constrain very light fuzzy dark matter masses even by cosmic microwave background experiments or large-scale structure. And then for heavier masses, you have to go to increasingly more nonlinear, shorter scales, and then reionization, UV luminosity function, and finally also the Lyman alpha forest becomes more and more important in constraining heavier and heavier axion masses. And a slightly complementary exclusion can then be done from black hole superradiance, which excludes a mass range where the de Broglie or the Compton wavelength of the fuzzy dark matter particle is roughly equal to the Schwarzschild radius. and then superradiance can effectively occur. And by not seeing this effect, then we can exclude these higher masses here. These exclusions here, I should say, are only valid if indeed all dark matter is fuzzy dark matter. We just recently published a paper where we also considered mixed dark matter, and then these constraints are weakened. So what I will discuss here is basically what I was looking at for the last few years, basically quantifying fuzzy dark matter halo dynamics, which means the radial density profiles, the cold dark matter velocity dispersion versus the fuzzy dark matter granular structure that we saw before. So indeed, velocity dispersion results in this granular structure in fuzzy dark matter. So there's a one-to-one correspondence. I will come to that in a minute. And then finally, these solitonic core dynamics, so the growth, the oscillation, the equilibration, and so on. I will do so in actually two different scenarios. So one is, I will start with the pure fuzzy dark matter scenario, and then continue with the fuzzy dark matter plus baryon scenario. And we'll just briefly mention the mixed dark matter case with fuzzy dark matter and cold dark matter, because Mattea, who is also giving a talk here, she will actually then present our very recent paper on this mixed dark matter stuff. And I did all these analyses using various different numerical techniques, namely adaptive mesh refinement structures, where we use hybrid particle and grid method, and then finite differencing, spectral methods, and also n-body algorithms. So a huge variety of different numerical schemes. So let me come to the pure fuzzy dark matter case that we investigated with a hybrid method, where hybrid means that basically in the volume filling, in the cosmological volume, we use particles. It's basically the background that you can see here with the large scale structure. And then we did a zoom in simulation into a single pre-selected halo, and that we refined very strongly. And then on the finest level, we use a finite difference scheme. And here in the inlay, you can see this finest level with the granular structure again, and then the soliton in orange in the center. And you can also see here, so the entire box was on a megaparsec scale, but then we really zoomed into a few kiloparsecs. And actually the effective resolution is then only just a few parsecs in the very center of that halo. So how do we do these? Or how do we combine these two schemes? As I said before, we use adaptive mesh refinement. So that's basically that we have regions with more or less fine grids. And especially we select one halo, and then there we have a very fine grid, and all the rest we leave basically unrefined. The particle method on the lowest levels, and then only on the finest level, we use finite difference. And then the important thing becomes boundary conditions between these methods. So both initial conditions and then also spatial boundary conditions. And in order to communicate between these two methods, we make use of the Madelung transformation, which basically is just representing our wave function in polar coordinates. And if you then plug that into the Schrödinger equation, you realize that it becomes a Euler equation with this infamous quantum pressure term, where the gradient of the phase is associated to the velocity. And therefore, our initial phase, as can be seen here in the second equation, can be constructed from the density field simply by using the divergence of the velocity and associating that to the Laplace of the phase. And then we use the Laplace operator of the phase, and then we use the Poisson solver in ENSO or NUX or another cosmological code and reconstruct the initial phase from that. And then this phase is evolved in time with this third equation. And this is evolved for each particle. So we use mainly an n-body scheme, but it's basically extended in the sense that each particle not only has a position in phase space and a mass, but now also a velocity and a phase. And as I said here, we can reconstruct this initial phase at the very beginning and then evolve the particles phase in time using this evolution equation. And then whenever we want to reconstruct the wave function from these particles, either as initial conditions at some lower redshift or then boundary conditions for even lower redshifts, then we use the classical density as a proxy for our amplitude. So the amplitude of our wave function is just the square root of the classical density. And the phase at each grid point is a weighted average over all the particle velocity phases in the surrounding. So since we use the classical density and only this weighted average for the phase, there's no gradient energy and interference effects considered at the reconstruction point. So basically that means that we have to go far enough or to high enough redshifts so that gradient energy is still subdominant because there's not so much velocity dispersion yet, so that we don't see strong interference effects anyways. And also for the spatial boundary conditions during our simulation, we have to go far enough outside of the halo in order to still have this continuous inflow and not the strong velocity dispersions around the virial radius. So we have to place our boundaries far enough away from the virial radius of the pre-selected halo. Sorry. Okay, so that's basically what we did, and we simulated that. And these are the first results that I want to show here. Namely, here in the upper left, you see the velocity spectra for both fuzzy dark matter represented by the solid lines and cold dark matter represented by the dotted lines for 3 different halos that we investigated. And as you can see here, they all lie very much on top of each other and actually match the theoretical expectation of a Maxwellian spectrum. So that is very reassuring. And it also shows that indeed the granular structure from which we can then extract this velocity dispersion using the Wigner transformation indeed has a one-to-one correspondence to the velocity dispersion. So it's really the granular structure that we see is the interference of plane waves with different wave numbers, where these wave numbers are indeed distributed according to the cold dark matter expectations and are distributed according to the Maxwell spectrum. Then we can also look at the central density at the upper right here, and we see that the center, so the core in the center, so the central density basically covers the also the central density in the core fluctuates, and we can use a Fourier transformation in time to see that it indeed fluctuates on a characteristic time scale. And this frequency is indeed given by the gravitational time scale of that soliton. So it's inherent quasi-normal mode, and it fluctuates on that time scale. And then the amplitude of the fluctuation is determined by the perturbation that the soliton feels from its halo surrounding it. Then finally, on the lower right, we see that the core is the only granule that is indeed virialized, while all the other granules are not self-bound. So the potential energy is much smaller than the kinetic energy. And therefore, here on the lower left, we see that they indeed fluctuate strongly on the de Broglie time. So they pop up into existence, and then after one de Broglie time on average, they evaporate again and then form and so on. So it's a very dynamic process. So that was the pure fuzzy dark matter case. And then in a second step, we added baryons to that and basically redid the same analysis that I showed you before, and finding quite similar results. So here on the left-hand side, you see the radial density profiles at 3 different redshifts. In green, basically what we had before, just fuzzy dark matter, and then in orange, cold dark matter with baryons, and in blue, the most interesting, so that's fuzzy dark matter with baryons, and then in gray, the gas. And what you can see is that it is initially suppressed compared to cold dark matter, but then, especially for lower redshifts, the solitonic core forms again, and then it is even in the center, it's even higher than cold dark matter. I mean, that's not a cusp here, it's again a core, but we have this very prominent core actually. In this case, it is not well fit by the standard soliton profile, which you can see here in black. But due to the additional gravitational potential from the baryons, it is actually altered. And this new effective profile that accounts for the external gravitational potential due to the baryons and stars and so on is here given by the red curve. And as you can see here, while the black curve doesn't match very well the numerical results, the red curve is actually very much aligned with our fuzzy dark matter plus baryon case in blue. So that's reassuring. So we, again, even with baryons, found a new ground state, which now is this modified solitonic core state. And indeed, even with a lot of baryons here, you can see that the baryonic density even exceeds the cold dark matter density in the center. Even in this extreme scenario, fuzzy dark matter actually develops this ground state. We can then look at velocities, and we namely look at velocities at 3 different radii. So at the soliton itself, then its immediate surroundings, and basically at the virial radius. So this is the outer region in the dotted lines. And as you can see here, for fuzzy dark matter only simulations, they all are pretty much on top of each other. So there's a slight difference, but in principle, they are flat over time or over redshift here, and all pretty much comparable with each other. And that's actually what also Schwabe et al. In their Nature paper from 2014 found, that the virial velocity can be identified roughly with the core velocity. This changes if you add baryons, because these baryons then heat up the center over time. You can see here, but the soliton and its surroundings stays in kinetic equilibrium. So the solid blue line and the dashed blue line are basically very much aligned with each other, and also follow nicely the cold dark matter reference simulation. And again, we could look at the oscillating core and Fourier transform the central density and find again that it oscillates on a characteristic frequency, which now is again the gravitational timescale, but where now gravity is sourced not only by fuzzy dark matter, but also the baryonic content. So it's the sum of those two densities now. But yeah, in principle, again, very consistent. And finally, now just a month or two ago, we published the third step, basically, which is then mixed fuzzy and cold dark matter, and simulated that with or studied that with spherical collapse, and used our new code AxioNyx, which again is a adaptive mesh refinement simulation for, in this case here, for mixed dark matter, where cold dark matter is evolved by the n-body scheme that is pre-implemented in this cosmology code Nyx. And then fuzzy dark matter we evolve on the root grid with a spectral method, and then on final levels that are not periodic, and therefore we cannot use spectral methods, then there we use finite difference methods. And in principle, the idea is to include also baryonic physics, but for that we still need to develop some of the feedback modules. So Nyx has already a hydrosolver pre-implemented, but there's not yet all the feedback in there. So that's something for the future. And here you can see an example of one of our spherical collapse simulations, where here on the upper left, you have the full simulation, and then we zoom into the central part that is more refined, and you start to see here on the right the granular structure. And if you zoom into the very center, then even the core is very prominently visible. And we basically redid these quantitative analyses that we did before, adding some new stuff that evolved with when considering mixed dark matter. But that will be something that Mattea will be talking about in her talk, so I will not present too much of what she will tell you anyways. So thanks for watching, and I will stop here now and then potentially answer questions during the discussion session. Thanks.